When you run a database across multiple machines, you are immediately faced with a fundamental constraint that no amount of clever engineering can fully escape. The CAP theorem names that constraint and forces you to think clearly about the trade-offs baked into every distributed storage system you will ever build or choose. The moment you replicate your data across two or more machines, you have bought yourself fault tolerance but introduced a new problem. Those machines must agree on what the current value of any piece of data actually is. Agreeing requires talking over a network, and networks are not perfectly reliable. Packets get lost, switches fail, and entire data center links go dark. That gap between what you need, perfect agreement, and what the network gives you, imperfect communication, is exactly where the CAP theorem lives. Think of two bank tellers who share a single customer account but work in separate rooms connected only by a phone. As long as the phone works, they stay perfectly in sync. The moment the line goes down, each teller faces a stark choice: turn the customer away until communication is restored, or go ahead and process the transaction and accept the risk that the other room has already done something conflicting. That dilemma, refuse service or risk inconsistency, is the heart of the CAP theorem. The CAP theorem, stated by Eric Brewer, and later proved formally, says that a distributed data store can satisfy at most two of three properties simultaneously. Consistency means every read sees the most recent write, every node agrees on the current value. Availability means every request receives a response, never an error or a timeout. Partition tolerance means the system keeps operating even when the network link between nodes breaks. The critical insight is that network partitions are not optional. They will happen in any real system. That makes partition tolerance effectively mandatory, which means your real choice is always between consistency and availability. Here is how the trade-off plays out in practice. A network partition occurs, node A and node B can no longer communicate. A client then writes a new value to node A. Because the link is broken, that write cannot propagate to node B. ACP system, one that prioritizes consistency, will refuse requests to node B until the partition heals, guaranteeing no stale data is ever returned. An AP system, one that prioritizes availability, will let node B keep answering requests, but the data it returns may be out of date. Neither choice is wrong. They are different promises to your users. A CP system like HBase or Zookeeper will return an error or block during a partition rather than risk serving incorrect data. That is the right call when correctness is non-negotiable. Think bank balances or stock levels. An AP system like Cassandra or CouchDB, in its default mode, keeps answering every request but may give different nodes different views of the data temporarily. That is acceptable when a slightly stale social media post or a cached product description is far better than an outage. The key word is eventually. AP systems converge to consistency once the partition heals. The most important practical step is to ask, per data type, what the cost of staleness actually is. A slightly out-of-date tweet count is harmless. A stale account balance is dangerous. Many modern architectures do not pick one extreme globally. They route strongly consistent operations through a CP path and serve read-heavy, latency-sensitive workloads through an AP path. Whatever you choose, make the trade-off visible in your design documentation so that every engineer on the team knows which guarantee they are and are not getting. The CAP theorem is not a flaw to work around. It is a law of distributed systems to design with. Partitions will happen, so every system implicitly picks a side. The architect's job is to make that choice deliberately, document it clearly, and build the application layer to handle whichever guarantee is missing. Knowing CAP turns a confusing cluster of trade-offs into a clear, reasoned decision.